So let's consider the case of a point charge and a sphere surrounding the point charge. And I want to know what is the flux through that sphere. Okay, so I want to know what is the electric flux through the sphere. Okay, so the sphere is of radius r. So we got our point charge. We've got a sphere surrounding it, sphere of radius r, and I want to know the flux. Well, we know that the flux, the general form of the flux is going to be the integral E dot dA, okay? And the nice thing about this is that the electric field just goes straight out, okay? So that means the dot product is not an issue. So the electric field just integral E dA, because the dot product, it's just EDA, okay? And the electric field, if we're always the same distance away, some radius r, then the electric field is constant. Now, that would not be the case if the sphere was not centered on the charge. So if the sphere is not centered on the charge, the electric field is stronger on one side, weaker on the other side, so it would not come out of the integral. Well, we don't want to do that because that's tough. We don't want to do something tough. So we're going to make this simple. Well, what's integral dA? That's an easy integral. So that's just E times A. So A is going to be the area of the sphere. Okay. So the area of the sphere is 4 pi r squared. That's the area of a sphere. Not 4/3 pi r cubed, that'd be the volume, the area. So what about E? Okay, so the flux is E times 4 pi r squared, but E is going to be equal to, for a point charge, if we're some distance r away from it, we know the E is 1 over 4 pi epsilon naught q over r squared. Okay, yeah, I know. When I did this before, I wrote it as k sub b q over r squared, but I said that k sub b is the same as 1 over 4 pi epsilon naught. Turns out in this case, that actually makes it easier, okay? Because if I use this form of writing it and I plug in, I have 1 over 4 pi epsilon naught q over r squared times r squared, times 4 pi r squared. Okay, so the 4's cancel, the pi's cancel, the r squareds cancel, and that's just q over epsilon naught. Okay, so that would be the flux. So we have here, for this sphere of radius r, I can call it R1, the flux in sphere 1, okay, so for sphere 1, the flux is going to be equal to q over epsilon naught. Now, what if I had a bigger sphere of radius R2? What would be the flux in there? Well, you look at that equation and change the R in it. Guess what? There's no R. So the flux in the big sphere, for sphere 2, is also Q over epsilon naught. So remember, the flux is kind of like the charge, or rather the electric field going to the surface. So that means if I have any sphere in between here, then the flux is going to be Q over epsilon naught. Now here's the next question. What about a cube sandwiched between the spheres? Now, the problem is that with a cube, if you had a charge in there, the electric field goes out. So when I do the integral, so the flux is going to be the integral of E dot dA. Now the problem is E is different at every spot along the surface here because it's a different distance from the center. The dot product is different everywhere because it's a different angle. So that makes that an incredibly nightmarish integral to do. So how do you do a nightmare integral? Well, you don't. You avoid it. Okay. So integration by avoidance. Okay. So how do we do that here? Well, we look at it and say, well, the total flux of this sphere on the inside is Q over epsilon naught. the total flux on the sphere on the outside to Q over epsilon naught. So the electric field always starts and stops at charges, and there's no charges between the inner sphere and the outer sphere. Therefore, you've got to have the total flux is the same. So that means the flux in the sphere is going to be Q over epsilon naught. Well, if I had a cylinder with a charge on it, and I want to find what is the flux there. Well, that would be incredibly nightmarish to do the integral. So the integral, the integral for the flux here, the integral for the flux, the electric flux, is integral E dot dA, and so it's going to be a total nightmare. Okay, but we don't have to worry about that, because I can imagine a little small sphere that fits completely inside the cylinder, and I know the flux there is Q over epsilon naught. I can always imagine a giant sphere outside of any surface, and the flux in there is Q over epsilon naught. So that means the flux through any surface in between is also Q over epsilon naught. Okay. So I avoid the bad integral by knowing that I can do these trivial things inside and outside, and it's got to be the same. Well, what this means is for any surface, even some nightmarish surface here in 3 dimensions, and I put an electric charge somewhere in there, I can always imagine a little sphere around that electric charge, a big sphere surrounding the entire thing, and so the flux is always going to be equal to Q over epsilon naught. Well, back here to my sphere. So we have here, okay, what if I wanted to imagine off-centered? Remember I said that's a very difficult integral to do? Well, that's easy. I imagine there, and I imagine a really big sphere there, okay, and so that we always get the same thing. So this off-center one has to be the same flux as the little one and the big one, so that means the flux is Q over epsilon naught. Okay, you see a pattern here. Now, what if I had a sphere here and I had a charge there? Well, if I imagine here, the flux through that sphere is Q over epsilon naught. So if I imagine another sphere there, that flux is Q over epsilon naught. So that means it's the same flux. But for the thing in here, that means the electric field goes in one side, out the other side. And so as we did in an example before, that means the flux in there has to be 0. So there's still charge here, but the charge is not inside this sphere, and that's why the flux is 0. So we can generalize this now to say the electric flux, which is the same as the surface integral E dot dA, is equal to the enclosed charge over epsilon naught, where this is the flux through a solid surface, a solid 3-dimensional surface. Okay, this Q is the charge that is enclosed inside of that solid surface. So that would tell us that the flux through any solid surface is going to be the enclosed charge over epsilon naught. And so we call this Gauss's law, after Carl Gauss, who worked out this relationship right here. Gauss's law turns out to be a shortcut to figuring out a lot of the things that we did in Chapter 2. And so we'll start showing how to use Gauss's law in the next several example problems.